In this video, we'll take a look at a third example of a hypothesis test involving a population proportion. A statewide study in Colorado recently found that about 64% of adults in Colorado had moderate to high, in other words, over $500 in credit card debt. A policy analyst in Kansas believes that the rate, or in other words, the population proportion, of moderate to high credit card debt among adults in Kansas is significantly different from the rate of moderate to high credit card debt among adults in Colorado. The policy analyst surveys a random sample of 1,400 adults in Kansas and finds that 868 out of the 1,400 adults have moderate to high credit card debt. Is there sufficient evidence to conclude that the rate of moderate to high credit card debt among adults in Kansas is significantly different from the rate of moderate to high credit card debt among adults in Colorado? Use an alpha of 0.10 level of significance. For the solution, I'm going to start with that initial step 0, which is to summarize the information and identify the point estimate. So just in summary, in the description of this hypothesis test, the proportion of adults with moderate to high credit card debt in Colorado is 64%. The policy analyst took a random sample of 1,400 adults in Kansas, and these were the results of that study in Canvas. 868 adults had moderate to high credit card debt among that sample of 1,400. So that comes out to a sample proportion for Kansas of 0.62 when you divide 868 by 1,400. The sample proportion for moderate to high credit card debt in Kansas, the 62%, which was the sample proportion, is different from the population proportion for moderate to high credit card debt in Colorado, 64%. There is some difference, and that does seem to support the policy analyst's hypothesis. However, we will need to test whether that sample proportion from adults in Kansas, the 62%, is significantly different and therefore sufficient to support the policy analyst's hypothesis. Step 1, state the hypotheses. This is another hypothesis test involving a population proportion, so once again we'll use P to represent that, and P in particular represents what is unknown in the hypothesis test. The unknown in this hypothesis test is the population proportion, or the rate of moderate to high credit card debt among adults in Kansas. What is known is the rate of credit card debt in Colorado, that's 64%. And in symbols, the hypotheses can be written this way. The null hypothesis would be that the proportion of adults in Kansas with moderate to high credit card debt is just the same as the proportion of adults in Colorado with credit card debt. And then the alternative is that the proportion of adults in Kansas with credit card debt is different from the proportion of adults in Colorado with credit card debt. And notice that the symbol here is going to be the not equal to, and the not equal to is used when the hypothesis is asking if there is a difference. In fact, the key phrase would be this phrase here, significantly different. If you see a phrase like that on a homework or test, then in your hypothesis you'll be using the not equal to symbol. And again, on the homework or test, or quiz or in your own research, when you write the hypotheses, it's sufficient just to write them using symbols. But again, in the lecture notes, I've written sentences to describe the null and alternative hypotheses. We'll move on to step 2. Step 2 again is to verify the requirements for this hypothesis test. And in this lecture, I won't go into detail on step 2. It's very similar to the very first example we did in the first 2 videos. But I'm going to go on to step 3, test the hypotheses. And there are a couple different approaches that we'll take a look at. The first approach to testing hypotheses is the classical or the test statistic approach. If you're doing this approach, the first thing that you'll want to do is to sketch out the normal probability curve, then use a table to find the cutoff values for the regions that represent unusual study outcomes. We'll want to make a note that this is a two-tail test, because in the alternative hypothesis, we're using the not equal to symbol. Also note that the alpha here is 0.10, that's the level of significance, and that also is the area under both tails of the curve. Here's what the normal curve would look like. This is a two-tail test. The alpha is 0.10, that's the area under both curves, which means that under one curve, the area is half of that, 0.05. So you could think of it that way too, is that each tail has an area of 0.05. We'll want to find the values of these two cutoff values, and so we'll go to table 5C below table 5. Here's table 5C. This is a two-tail test. The alpha is 0.10, and the cutoff values are plus or minus 1.645. So 0 is in the middle of this standard normal distribution curve. The negative 1.645 would be this left boundary for the left tail, and then the positive 1.645 would be the boundary for the right tail. The next thing that we'll do is calculate the test statistic. Use this formula for the test statistic. This time the p sub 0, the value of the null hypothesis proportion, is 0.64. Sample size is 1,400. Sample proportion was calculated earlier. It came out to 0.62. Put those numbers into the formula and it comes out to negative 1.559. The last thing is to determine whether this test statistic is inside the critical tails of the curve or outside the critical tails. So inside the critical tails would mean that it would fall either in this tail or this tail. Outside the tails would be if it falls somewhere in here in between. And again, remember that if the critical test statistic falls in one of these critical tails, if it's here or here, that means that our study's results are unusual and significant, and you would say that you reject the null hypothesis. On the other hand, if our test statistic is outside the tails, somewhere in here, then that means that our results are not significant, and we would say that we do not reject the null hypothesis. Again, our test statistic was negative 1.559. Negative 1.559 is just outside of the left tail. It's maybe about here, negative 1.559. And that means that this particular study's results are not significant. And so we would say that we do not reject the null hypothesis. Another approach is the p-value approach. So if you're doing this approach, remember that you first calculate the p-value. On the Casio calculator, you would take these steps, go to the 1p function, put in these values. One thing to note is that now you're using not equal to for the inequality of the alternative hypothesis. On the TI calculator, same steps as before, except again, now you're putting in the not equal to for the alternative hypothesis value. When you do that, the p-value comes out to 0.1190. So what's the meaning of this? So in this case, that p-value, the 0.1190, is the probability that 868 out of 1,400 randomly selected adults in Canvas would have moderate to high credit card debt, assuming that the null hypothesis, that the proportion P is equal to 0.64 is true. In other words, assuming that the rate of moderate to high credit card debt among adults in Kansas is the same as the rate of moderate to high credit card debt among adults in Colorado. The next thing that we would do now is to compare the p-value to the level of significance. Keep in mind that these are the same conditions for when you reject or not reject the null hypothesis. If the p-value is less than alpha, then you reject the null hypothesis. If the p-value is greater than alpha, then you do not reject the null hypothesis. For this study, our p-value was 0.1190, the alpha was 0.10, and that means that the p-value is greater than alpha. And so since the p-value is greater than alpha, that means that this study's results are not unusual and not significant, and we would say that we do not reject the null hypothesis. There's a third approach that you can take to testing this hypothesis, and it's called the confidence interval approach. The confidence interval approach is most easily applied to two-tail tests. You can do a confidence interval approach for a left tail or right tail test, but if you try it for a left or right tail test, there are a couple extra steps that you would need to take. But for a two-tail test, there are not really any extra steps. The first thing you would do is to construct the confidence interval, and before doing that, you'll have to figure out what is the level of confidence. Well, the level of significance is alpha equal to 0.10. Remember that that's the area under the tails of the curve, and that corresponds to a confidence of 1 minus alpha. If you do 1 minus alpha, which is 1 minus 0.10, we'll get 0.90. That represents the level of confidence. In other words, that's 90%. So 90% is the level of confidence. To calculate this confidence interval in this lecture video, I'll just be referring to the calculator steps. But again, you could use a formula if you wanted to. So here are the calculator steps on the Casio, and also the calculator steps on the TI. These are the same steps that you probably saw in section 9.1. And the result comes out to this confidence interval, 0.5987 and 0.6413. The next thing that you want to do is locate the null hypothesis value, the p sub 0, with respect to the confidence interval. If the confidence interval is entirely higher or lower than p sub 0, that means that your study's results are significant and you reject the null hypothesis. On the other hand, if your confidence interval contains p sub 0, that means that your results are not significant and you do not reject the null hypothesis. For this study, the confidence interval does contain 0.64. 0.64 is within this, and that means that our results are not significant and we do not reject the null hypothesis. So step 4 is to state the conclusion. Our conclusion is that we do not reject the null hypothesis, and that means that there is not sufficient evidence to conclude that the rate of moderate to high credit card debt among adults in Kansas is significantly different from the rate of moderate to high credit card debt among adults in Colorado.